Thanks. Again, I'm working on the Lake Superior ecosystem model, and before I really get into this, I do want to thank my co-authors and everyone else that has helped. This is a multi-agency collaboration between members at the University of Minnesota Duluth, the EPA in Duluth, the U.S. Fish and Wildlife Service, and the USGS in Ashland. So, brief outline, I'm just going to very briefly give an update on the current status of the Lake Superior ecosystem, looking at abundance and harvest trends. Then I'm going to get into the EcoPath model and then EcoSim. Like I said very briefly, we've seen some declines in the pelagic or the prey fish community population throughout Lake Superior, and here we have just the USGS nearshore bottom trawl survey. The giant blue area is our pelagic prey, or is our prey fish, our ciscos, bloater, kai, whitefish. The red is our piscivores, and the black dashed line just represents our harvest, and that is like-wide harvest of all fish. So we've been seeing some declines in our cisco, bloater, kai, and deepwater sculpin populations, and our piscivore populations have been relatively stable. Our lean lake trout, ciscoette, burbot, and this is happening at the same time where we're actually seeing in recent years an increase in harvest throughout Lake Superior. So with this model, we're really interested in quantifying the ecosystem trends and to ask how has the Lake Superior ecosystem changed between 2005 and 2016. Like I said, the survey data and all of the presentations we've seen, or a lot of the presentations we've seen so far, suggest that we've seen declines in the prey fish community, and we've seen relatively stable lake trout populations. So what happens if these trends continue? And alternatively, what happens if some of this effort actually increases? So our objectives were to build a Lake Superior ecosystem model to quantify how the ecosystem has changed since 2005, and then to make predictions into the future. So what happens if we continue with the status quo, if we continue our 2016 harvest trends? What happens if we double the fishing effort? And in this case, we're going to look at what happens if we double the coragonid fishing effort. We did this using EcoPath with EcoSim, which is one of the most widely used ecosystem models. And EcoPath describes our food web structure, and EcoSim is our time series dynamics. So I'm going to jump right into EcoPath. So again, it's describing our food web structure. So we parameterized this for 2005, 2006, which was our first lake-wide sampling, and this sampling had surveys from everywhere from the phytoplankton all the way up through our lake trout. This model focuses on biomass generally in waters greater than 30 meters deep, and we have it broken into two zones. We have nearshore waters and we have offshore waters. I apologize. The nearshore waters should be roughly less than 100 meters, and offshore is anything that is greater than 100 meters deep. The model has a lot of components. We have 17 fish groups, we have 8 macroinvertebrate and zooplankton groups, 8 microbial loop components, and then some of these are further divided into different age or size classes and nearshore, offshore components. I'm not going to get into this slide. These are just a list of our data sources that we've used to parameterize the EcoPath model, and we've tried to get everything from the Lake Superior, and if not, we try to borrow it from one of the other Great Lakes. Here is our current Lake Superior food web. On the bottom, we have our phytoplankton and detritus, and as we move up, we start including some of our zooplankton, the mysis. We get up into the prey fish. Then up on top, we have the ciscoette, the lean lake trout, and finally at the top, we have our sea lamprey. And the size of the box just kind of describes the total biomass in that group. And we have this model, like I said, broken up into general nearshore, offshore. So on the left side, we're seeing that's generally nearshore. On the right side, we have our offshore food web. And then we also have this with benthic and pelagic. So on the outsides of the model, we have our benthic food web, and then in the middle, it's generally our pelagic. And if you follow up from the bottom, you can see for the nearshore, we have our benthic food web doesn't interact with our nearshore food web until we hit trophic level 3, which is about our mysis. You can see the same thing with our offshore food web. And for our benthic pelagic, nearshore offshore coupling, we don't see that until closer to the trophic level 4, which is primarily from Cisco. We have a lot of fleets in this model. Currently we have 33 fleets, and this represents the various commercial, tribal, recreational, and any kind of fleet with a different gear type. So in Wisconsin we have 11 different fisheries, and this is just so we can ask questions like, what if the Wisconsin Cisco fishery increases their effort? Or what happens if the Michigan whitefish fishery increases their effort? That's why we have so many fleets in this model. We also have a lamprey fishing fleet from the Fish and Wildlife Service, and we have an opportunity to explore 2 proposed fleets, lean lake trout and the Ciscoette. Next, we're going to get into our EcoSim, and EcoSim again uses our time series, and this module, it's the module that we use to simulate the temporal dynamics. We fit this to time series, and I'm not going to get into all of these different time series data, but suffice to say we have as many time series as possible. We have everything from lake-wide trends, U.S. waters, Ontario waters, and substantial harvest and effort time series as well. So the next couple of slides are going to show figures that are relatively similar. In this case, up on top we have large whitefish, and that's whitefish greater than 430 millimeters, Cisco greater than 300, and on the bottom we have bloater and kai, and those are all size groups. We have biomass over on the side axis in year from 2005 to 2016, I think, on the x-axis. We have all of the different surveys, and it doesn't matter what survey you're looking at. What lines you should pay attention to are the solid black lines, and the dashed black line, the solid black line is our path with EcoSim prediction. The black dashed line is just the average over all of our surveys. So really what we're looking for is how well does this black line capture those trends from all of our surveys. So are we doing a decent job? Are we kind of in the middle? Or is our EcoSim not really estimating and following those trends? So for our whitefish and Cisco, we can see that, yeah, we're generally following these trends. We're predicting a relatively stable population for both whitefish and Cisco. If we look on the bottom, we have bloater and kai, and we're predicting some declines in both of these populations, which we see in our surveys. For a couple other prey fish, we have large smelt, greater than 130 millimeters. We have nearshore sculpin and deepwater sculpin. For our smelt population, we have a highly variable population that is in general increasing. For nearshore sculpin, we're seeing a decline in those populations. For deepwater sculpin, we're remaining relatively stable, and then we start to see a decline at the end. For our piscivores, burbot, lean lake trout greater than 500 millimeters, and Ciscoette greater than 500 millimeters. For burbot, we're seeing a general increase in our population, followed by slight stabilization or decrease just in the last couple of years. Lean lake trout, we're predicting a very stable population, and Ciscoette is stable with possibly a little bit of a decline in there. So just a quick recap on these. So we're seeing declining populations in kai and deepwater sculpin that are over 60%. For bloater, nearshore sculpin, Ciscoette, we're seeing somewhere between a 20 to 30% decline. For rainbow smelt and burbot, we're seeing increases, and we're seeing relatively stable lake whitefish, Cisco, and lake trout populations. And those lake whitefish, Cisco, and lean lake trout are anywhere from 11% increase to a 9% decrease over this time. If we project these through time, here we have the exact same figure. It's now just projected from 2005 to 2055, And again, the solid black line is our status quo. So what happens if we continue with the 2016 harvest trends? And the black dashed line is just our average from the surveys from 2005 to 2016. And the blue is what happens if we double our coregonid fishing effort. So for whitefish, we see our population is remaining relatively stable if we continue with our 2016 trends. If we double our coregonid effort, as expected, we're going to see a decrease in whitefish population. For Cisco, we're staying relatively stable with both options, whether we continue with the status quo or double the coregonid effort, and that's just because we're not harvesting a ton of Cisco lake-wide. In certain areas, we're harvesting more than others, but lake-wide, the trend is relatively stable. For bloater, we see we're continuing the population decline, and it's getting a little bit more stable after about 2030, and there's not much of a difference between the ecosystem predicted and if we double the coregonid effort. For Kai, we see our population start to rebound after about 2015, 2020, and after about 2030, we see an increase in our population if we have, or higher population if we increase our coregonid effort. For the other prey fish, smelt, sculpin, smelt, we see our population just kind of remain stable at a higher level. There might be a slight increase if we have double coregonid effort. For nearshore sculpin, we see that population continues to decline, and for deepwater sculpin, it rebounds after about 2020 to roughly the current state. For piscivores, burbot is the only really odd one that we see that doesn't, the long-term trends don't really follow with the 2005 to 2016 trends. We actually see that population decline if we continue with the status quo, and it ends up increasing then after about 2020 or so if we have a double coregonid effort. For lean lake trout, it remains relatively stable. There is a very slight increase on that. And then for Ciscoette, we're seeing that the Ciscoette population continuing to decline. And I do want to note that there might be some incidental harvest on lean lake trout or Ciscoette that I might not have captured with this model that might not represent the increased in coregonid effort. So these trends might not be exactly right. And again, these are lake-wide trends. Things that happen in local areas, so if we're talking about just Wisconsin waters, we might see different trends versus the whole lake-wide. So long-term trends appear relatively consistent with the 2005-2016 trends if harvest remains at the 2016 levels. This is with the exception of burbot, which we saw beginning to decline after about 2014, and this was from increased predation. We see Ciscoette, bloater, kai, and sculpin population declines, and relatively stable populations of whitefish, Cisco, and lean lake trout. There might be some increases in lean lake trout with this model, and we also see increases in rainbow smelt. If we double our coregonid effort, we expect to see smaller populations of whitefish, slightly smaller of deepwater sculpin and Ciscoette. We see relatively larger populations of smelt, burbot, and kai, and other species are predicted to remain relatively stable. But I do want to caution that these are lake-wide trends, and these trends might not represent what happens in a given management unit, which is where one of the areas I want to take this model into the future. It's more looking at this spatial dynamics. So if we can take the current ecosystem model and incorporate those spatial dynamics by moving it to ecospace. Just briefly, one of the main problems that I see with this model is that we're not seeing these declines in Cisco. These Cisco declines are appearing in some of our surveys, but there is also a lot of noise throughout these surveys. I do also want to note that the data we have was weighted using standard error and area sampled. So surveys that we have from a lake-wide survey, such as the CSMI, have more weight than something like the Wisconsin Gillnet survey, because they're sampling such a small area relative to the lake-wide. The Cisco recruitment dynamics, we're not predicting the highly variable recruitment with this model. We're predicting a relatively consistent recruitment, which is not probably very accurate. And I have been recently working on getting the model to include that highly variable recruitment, and I couldn't present on that today because I finally figured that out about 3 days ago, and that should help, or I'm hoping that it'll help to capture those expected declines in Cisco. But overall, this model does appear to capture those biomass trends across the trophic levels. I didn't show you the phytoplankton and zooplankton trends, but they're pretty much exactly the same. We are capturing those ecosystem trends. With that, I would like to thank everyone that has helped with this, and everyone that helped either collect or compile the data, and the members of the Lake Superior Technical Committee. And I would love to take questions if there's time.